Hey, this is the fourth short video out of chapter 4 in our physics class. We've looked at the fact that acceleration is caused by forces. We've looked at friction. We've looked at mass and weight. Now it's time to look at Newton's second law. Newton was the one who realized that it's the connection between force and mass that produce acceleration. So Newton takes credit for that. The complicated way to say it is that the acceleration resulting from a net force is directly proportional to the net force in the same direction as the net force and is inversely proportional to the mass. So Newton is comparing acceleration to the net force and the mass. All right, is this starting to look familiar? And when you take away all the words and abbreviate it, we're going to say force is equal to the mass times the acceleration. That, my friends, is Newton's second law. That's why I've got the two fingers pointing up here. If we divide both sides by mass, that leaves us with the idea that we can estimate an acceleration as the force divided by the massiveness, the force on an object divided by the massiveness of that object gives us the acceleration. These are vectors. So they're going to be operating in the same direction. That is Newton's second law. Acceleration is the net force divided by the mass. Okay? If our acceleration goes up, or if our net force goes up, our acceleration goes up. If our mass goes up, our acceleration goes down, becomes less. All right? That's why we say these are directly proportional, and this one is indirectly proportional. Let's try an example on this thing. I have some bricks that are identical, and I'm equally strong in my left hand and my right hand. All right? And I can always push at the same amount of force. So I have my hand, I'm pushing, and it's causing the brick to accelerate. All right? If my force doubles, because I'm going to push with both hands instead of one hand, then I get twice as much force and twice as much acceleration. But when I double the massiveness of the load, if I've got twice the mass and twice the force, twice the push, I'm going to end up with the same acceleration that I had here. If that doesn't make sense, rewind and look at that again. Let's look at another circumstance. Same thing, one hand, one brick. I push it, it moves, it accelerates. So it moves at an increasing velocity. It starts slowly and it moves faster. If I've got double the bricks, If my bricks become double, but my force remains the same, my acceleration is going to go down by half. All right? If my force stays the same, but now my mass is triple what it was originally, then I'm only going to get 1/3 of the acceleration I got originally. All right, consider that I'm hauling some stuff. Maybe it's medieval times. I'm hauling some goods to market. I've got a horse. He can pull at 1 horsepower, and I have a cart. Okay, my cart going to the market is full of goods, and my horse can pull it. My cart leaving the market, thankfully, has gotten rid of a lot of goods. So the mass of my cart leaving the market, or continuing on to next day's market, is half the mass of when we came in. Same horse, pulling with the same level of force. What changes with the acceleration of the cart when it's full versus when it's half the mass? Cart acceleration stays the same. The cart acceleration is half because the mass of the cart is half. The cart acceleration doubles, or we can't predict the change of it. Think about it. Same horse pulling a cart. The horse pulls the cart later. The cart is half the mass. What does the acceleration look like? Well, of course, when the horse is pulling less mass, he's going to pull at twice the acceleration. A lighter cart, the same horse can pull faster. All right. In our case, the acceleration originally is that, and then after we're done at the market, our acceleration is force times 1/2 divided by 1/2 the mass. So our acceleration is doubled. The horse can pull the lighter cart, the less massive cart, faster. Okay, you and your neighbor both have a cart. However, to travel to market at the same time, your steady horse is good on your cart, but your neighbor needs 2 of these horses to pull his cart, and you are making your accelerations be the same. Why does his cart need 2 horses and yours only needs 1? Why might that be? Is it that the mass of one cart has doubled the other? That there's a force that we haven't taken into account? That the road is not level? Or that friction has reversed the direction? Well, in this case, one cart, your neighbor's cart, is just plain harder to pull. It's harder to pull because it is more massive. So the load that you are carrying, you're maybe carrying a load of feathers to the market, and your neighbor is carrying a load of gold to the market. There's just more stuff in his cart. His cart is more massive. All right, our next conversation is going to be a review of free fall. Free fall, just like we have looked at in the previous chapter.